Before we start discussing the potential energy caused by electric fields, it's probably a good idea to do a bit of review and look at the potential energy of a gravitational field. The potential energy is related to the work done by a conservative force. A force is conservative if the force depends only on the position of the object, or so if you know the position, you know the force. Gravity and electrostatic forces are good examples of conservative forces, while friction or air resistance are good examples of non-conservative forces. To remind you how this works, we have someone pulling on a pulley that is lifting up a heavy object. The work is being done by the person, the tension on the object is pointing up, and the object is moving up, so the work done by the tension is positive. However, the work done by gravity is negative. That is because the gravitational force is pointing down while the box is being lifted up. So, we see that when an object is being moved through a gravitational field, the change in the potential energy is equal to the negative of the work done by the conservative force. So, if you push a box up in the air, the potential energy is increasing because when you release the box, it will fall. That means that the work done by gravity is negative since the object was lifted against the direction of gravity. More quantitatively, the work done is the force times the displacement. So the force is the weight force, mass times gravity, and the displacement is the height, or by how much the weight has been lifted. We use g is equal to 10 meters per second squared, but we could also consider g to be the strength of the gravitational field, and we would then call it 10 newtons per kilogram. Both of these units are perfectly correct. So the change in potential energy, so U sub g, is equal to mgh, the mass times the gravitational acceleration times the height. That means when an object of mass m is lifted by h, when it is released, that potential energy is spontaneously converted into kinetic energy. The object falls, and we can find the new velocity using conservation of energy, where kinetic energy is 1/2 mass of the object times the velocity squared. The beauty of potential energy is that once you know the change in potential energy between 2 points, it does not matter what path it takes or how it got there. If you drop 1 kilogram weight by 1 meters, the weight will have 10 newton meters of kinetic energy, whether you dropped it straight down or if you tied it to a string and swung it. The fact that the potential energy changed by that much, as long as the energy is converted completely to kinetic energy, the kinetic energy is the same. So you have 2 problems to do. The first is the Atwood machine. In this case, we have 2 weights, one heavier and one lighter, and they're attached to the same rope, and then they're put through a pulley. So we want to know what will happen. Will the heavier object fall and will the lighter object fall, or will neither? If the heavier object falls, then the potential energy must decrease as the object speeds up, and then the kinetic energy must increase. The second looks at conservation of energy. We have an object with a mass m that falls the same distance in 3 different scenarios. One is dropped, one is slid down a frictionless surface, and the third is attached to a rope and it swings down the same height. Well, examining the forces can be a bit tricky here. In the pendulum and sliding case, finding the change in potential energy here is pretty straightforward. All you need to know is by how far it is dropped, and then you can find the change in potential energy. Since gravitational potential energy and kinetic energy are the only relevant forms of energy in this situation, we can then find the increase in kinetic energy. Okay, so you have some questions to do, and then next we're going to complete our comparison of gravitational and electrical potential energy.